This is Team Ben Squared, and this is our 4-bit ALU project. We were tasked with designing 12 different components. As you can see here, we even decided to tackle these two bonus problems down here, the Johnson counter and the shift rotate. Our board has 9 different switches to implement all this, so or 10 different switches, sorry. SW9 down to SW0, then we have 4 buttons, key 3 down to key 0. This right here is our board. And let's just start with our first component, which is the AND gate. This will just AND our bits together, which as you can see, zeros ANDed with zeros should be zeros. But if we have all ones, it will be F, which means 1, 1, 1, 1. And then let's say we AND 0, 1, 0, 1 with 0, 0, 1, 1, 1. This will just give us 0, 1, 0, 1, which is equal to 5. So as you can see, we can tell that the AND gate does work for this.
Alright. Next up we have the OR gate, and for the OR gate, we're also just using 2 4-bit vectors. So if we set everything to 0 and use the op select to turn everything on, 2 4-bit vectors that are all 0 and OR together is going to give 0. So then if you OR 1, 1, 1, 1 with 0, 0, 0, 0, you get 15 or F, and if I OR something like 10 and 13, 10 and 3, my mistake, it should be like 11, which is B, so you can see that the OR gate is also working properly.
Alright, our next component is the XOR gate. This will only output a 1 whenever one of the inputs is 1 and the other is 0. So when it's all zeros, it should still give 0, and then let's say that it was all ones. Whenever I select the opcode here, it should go back to 0. So let me go back to the start there, since I didn't actually have the opcode. See, it's all zeros, and then when we select all of these, it will go down back to 0. And then let's say we test 9 with 15. This will give us these 2 bits as 1, so 0, 1, 1, 0, which is equivalent to 6. So we can tell that our XOR gate is also working.
Our next component is the inverter. The inverter only takes in A as an input. So if I go ahead and put on the opcode there, the inverse of 0, 0, 0, 0 would be 15, and it gives F. So then if I do the inverse of 1, it'd be E, which is 14. If I do all ones, then it's going to give me 0. So the inverter is also working.
Okay, then our next component is the adder. This has one extra component that the other ones don't. It has this button right here as a carry in. So whenever I push this, actually let me select the opcode this time. Whenever I put in the carry-in, it should just add 1 to our total. And then let's do something like 3 plus 7. This should just give us 10, which is A. If we do the carry-in, it will be 11. And then let's say we have 6 plus 11. This should give us 17. As you can see, this little light right here is our carry-out. This light, whenever it's on, represents that there is 16, a value of 16 being added to the number displayed here. So this is 16 plus 1, which is 17. Then the carry-in would give us another 1. So as you can see, the adder does work.
Alright, for our next component we have the comparator. So it takes in A and B and compares which one is the high value and which one is greater than, equal, or less than. So if we go ahead and select our op here, and we compare, 1 to 0, then it's going to say A is greater because A is greater. Make it like this, A is still greater. If we set B greater, then it'll say B for B equal greater. If they're equal to each other, it'll put E, as you can see, across the board. So the comparator works properly.
Alright, our next component we just move this up. This one is even and is odd, or sorry, is even. Is odd is the next component. Is even just looks at A, and it just looks if the number is even or not. The opcode is this right here, so let's just select that right now. It will display an E whenever it's even, so right now it is saying that 0 is even, which we can confirm. This would mean 8's even, then we have 12 is even, then we have 14 is even. But as soon as we get to 15, it will display an F for false, and then as we can see, if we just go back through all this again, all of those were odd, and this was still displaying F, which means our is even is working.
Alrighty. Our next component is the is odd component, and this component does the opposite of the is even. It checks to see if A is even or odd, but it really is just checking if it's odd. So I go ahead and activate it with the op select, and right now it is even. So it's outputting F for false because it's not odd. If we make it odd, it'll produce O for odd. So any odd number is going to produce 0, and as soon as I flip this down, it'll produce F for false.
Okay, our next component is the shift right register, or just the shift right. This is the opcode for that. It's 1000. This has two bonus inputs. It has the left shift and the push value. Our left shift is where our most significant bit for B was, and our push value is at that second bit for B. And basically push value, that will be what we're pushing into our vector, whereas load shift was just if we're loading in whatever A is, or if we're shifting whatever A is. So right now it says zeros, but let's load in, actually let's just change our push value to 1. That should make it shift to the right with 1, it should be 8, and then it should be 12, and then 14, 15. There we go, and then if we shift in zeros, it should be 7, then 3, then, sorry, it should be 7, then 3, then 1, then 0, yeah. There we go, so we can see that the push value is working, and then if we want to test the load shifts, let's say we want to start at 9, we just press that up, and there we go, there's the load shift, and as soon as I change this back to shifting, this will shift this to the right with the push value 0, so it would go 7, and then, not 7, it would go 4, then 2, then 1, then 0. There we go, and then there is a reset for this as well. That's this button over here. If I just press this, it will reset it back down to 0, and nothing else will happen to the number. So as we can see, the shift right works.
Our next component is the shift left. It also has a load shift and a push value. It's just going to be shifting in the opposite direction. So if I give myself a load value of 0 and a push value of 1, and go ahead and put on the op select for this one, or if I go ahead and reset it, starting from 0, it'll shift left. So it goes from 1 to 3, 7 to 15, just like so. And then if I want to change the load value to 1, but I want to put in 10, I can go ahead and change A to 10 and put the load value, and it changes to 10, which is A. And then if I make the load value 0 again, and push value at 0, then it'll start counting down from 15.
Alright, next is our bidirectional PIPO shift register. This one has an extra input that our other two didn't. It has this direction right here. This is just to show if we're shifting to the right or left. So if direction is 1, it shifts to the right, and if direction is 0, it's shifting to the left. So right now we're pushing in zeros and we're pushing to the left. So let's say we want to shift to the right. with a push value of 1, that would be 8, and then it would be 12, then it would be 14, 15. So 8, 12, 14, 15. As you can see, that works. And then we start that reset button over here. If we just push that, resets it back down to 0. Goes 8, 12, 14, 15. Then let's say we want to go the other way. Well, not the other way. Let's say we want to push in zeros. This would be 7, then it would go to 3, then it would go to 1, then 0. So 7, 3, 1, 0. And then let's say we want to go to the left this time, and we want to shift a push value of 1. This will go 1, 3, 7, 15. Okay, hang on. I didn't actually have the correct module selected. I need to select the opcode, which is this button right here. That will put it back to the correct module. So let's say we want to push to the right with the push value of 1. That would go 8, then it would go 12, then it would go 14, 15. So 8, 12, 14, 15. This resets it back down to 0. Once we reach 15, if we push in zeros, it will be 7, then it will be 3, then 1, back down to 0. Then if we want to push to the left and a push value of 1, this will be 1, 3, 7, 15. Reset back down to 0, does the exact same thing. And then if we push in a value of 0, this would be 14, then 12, then 8. There you go, back down to 0. And let's say we want to load in something like 9. You just put in this load shift. The reset overwrites the load shift, but as soon as the clock hits, there we go. It goes back, and then it would be shifting to the left with a push value of 0. So this would be 3. Then it would be, not 3, sorry. It would be 2, 4, 8, 0. There we go. So as you can see, the people shift register works correctly when you use the actual opcode.
Alrighty. Next component is the bidirectional counter, starting with an input value. So for this one, we have a direction and a preset. The preset essentially is just going to load in a number, and then the direction chooses whether we are counting upwards or counting downwards. So if I go ahead and put in the opcode for this one, and you can see it's counting downward right now because my direction is at 0, which means it's counting backwards. If I flip the direction the other way, it'll start counting upwards. All the way back around to 0, and I can change the direction again, and it'll go from 0 back to 15. And then if I change this to 10 and turn on my preset, it'll load 10, which is A. And preset, turn my preset back down, and it'll count downward from 10 because the direction is still 0. If I reload my preset, change the direction, it'll count upward instead.
Okay, that's all the 12 components that were required to design, but we designed the bonus 2 components. We have a Johnson counter and a shift rotate. The Johnson counter uses a direction and a preset, so we can start at any number, and we can either count to the right or count to the left. And what this does, it just takes the inverse of whichever end you're counting from. So if we reset this back to 0, right now we are counting to the left. Let's change that so that we're counting to the right. So this would go to 8 next, and then it would go to 12, then 14, and then 15. Then that would go down to 4, actually, sorry. It would go down to 7, then 3, then 1, then 0. As you kind of already saw there, I kind of just mixed up my words. But yeah, 7, 3, 1, 0. And then if we switch our direction, it should follow that exact same pattern. So 1, 3, 7, 15, then 14, 12, 8, then back down to 0. As we saw, the reset works. But let's say we want to start at 9 again. We just flip this preset button here. We start at 9. We want to go to the right. And if we go to the right, this would go down to 4, and then it would go to, what's it called, 10, and then it would just keep going. So 4, 10, 13, then it just kind of cycles around there. I didn't remember every single one of those, but this does look like it is actually working, so that's good. Then our next component is the shift rotate. This uses an extra function called rotate. This is assigned to B's most significant bit, so switch 5. What this does is it kind of shifts the number to the right or left according to our direction. Right is 1, left is 0, and then whatever would have been shifted off the edge rotates back to the start whenever this rotate is 1. And then our preset obviously just presets a number and resets it back down to 0. So let's say we want to load in 8. Put the preset there. We want it to rotate, and we want it to shift to the right. So this will give us, it would give us 4, then 2, then 1, and then it just kind of keep doing that cycle. Yep, all the way back down to 8, and then if we want to change the direction, it will do the exact same thing, but backwards. And our push value is 0 whenever we're shifting, if that wasn't clear. So, yeah, you can see that the Johnson counter, or not the Johnson counter, the shift rotate works, and that's our entire 4-bit ALU. Thank you for listening.